Welcome to another Lunch and Learn webinar with WhyMaker. We are so excited to have you here with us today. My name is Alejandra and I'll be your host. Today, we are thrilled to spotlight one of our inspiring partners, the League of Young Inventors, an organization dedicated to empowering educators and students through hands-on STEM, engineering, and design thinking. The League of Young Inventors transforms classrooms into spaces where students think like real engineers and inventors, asking questions, testing ideas, solving problems, and building confidence along the way. Their work supports teachers with engaging standard aligned curriculums that make STEM meaningful, accessible, and fun. We are honored to be joined by Kira from the League of Young Inventors. Thank you so much for being here today. We are excited to learn more about your mission, your curriculum, and the impact you're making in classrooms across the country. And also a quick note before we begin, we will have time for a Q&A at the end of the presentation, so please feel free to drop your questions in the chat as we go, and we'll have a minute to read them later. So now, without further ado, Kiara, the floor is all yours.
Thank you very much. Hi, so yes, my name is Kira Newyart, and I am the Educational Director and one of the founders of the League of Young Inventors. So my background is actually in education. I was a teacher for a number of years. I taught preschool and I taught kindergarten and first grade. And then I got my PhD at Teachers College in philosophy and education, where my research mainly focused on progressive education. That was my real love. But I also grew up in the 1980s on a farm, and I grew up with two science educator parents. So I actually learned a lot of science as a non-science person, and I learned it both at home and at school, and much of it was project-based, which is, I think, one of the reasons why I feel so confident in my understanding of an ability to learn more about science as an adult. When I had my own kids, I have three in the New York City public school system. I actually realized that they weren't getting at all the same kind of learning at school that I had. And it really didn't sit right with me. That seemed like that was not something that I wanted my kids to never get to experience. So this is why my partner, Megan Eisen, and I started the League of Young Inventors. So we are a Brooklyn-based nonprofit on a mission to help elementary schools build a culture of invention and innovation. So we create hands-on learning experiences that tap into what kids already care about. So one of the things that we thought a lot about was, what sparks wonder for a 6-year-old? And beyond all the things that people normally think of, the real sense of deep wonder, a lot of the time it ends up being things like roller coasters or parachutes or things that adults might take for granted, like boats or bridges. I mean, these inventions have been around forever and they've fascinated kids for generations. And of course, science teachers have been building, floating boats and bridge units for a long time. But where our work departs from what comes before is how we frame these topics. So each unit is a 10-hour experience, and it's built around the engineering design process. And that's just that structure that helps students think like scientists and engineers. And in a few minutes, you'll see exactly what I mean. So a number of you have probably lots of experience running a hands-on project for your students, and I'm betting that a good number of you also spent your whole weekend prepping materials and rewriting lesson plans for these projects. And I did that too as a teacher. It was not fun. It was really frustrating. And that's really why our units are designed to be ready to teach. So we have slide-based lessons that you can edit and adapt. We have materials kits for up to 30 students. You just add scissors and tape. And we have PD that lets you experience the unit as a learner before you ever teach it. So you might be thinking, oh, slide-based lessons, everybody's doing that now. And it's true, but this is where we are different. So our slides, we do a lot of including things like short maker videos. Again, we know not every elementary teacher has an art or a maker background, And teaching a kid how to rip tape or fold a piece of paper isn't actually intuitive. And so we have that for teachers. We also build in visual explanations that connect what students experience to the science ideas themselves. And we do this because too often kids will experience or do something cool, but never understand fully why it worked. And then finally, our digital lessons are how we communicate the sequencing of the lesson. So they include starter scripts and guidance for managing materials and groups. We don't have a bulky teacher manual that you're going to need to lift up and then translate, because we really do believe that hands-on learning shouldn't really feel like chaos. So we currently have 10 units across 2 series. Our toy invention series you can see on the left of the screen, and our everyday engineering series that you can see on the right. And we also have more units in development. Our curriculum spirals from kindergarten through 5th grade so that students really get repeated experience with the engineering design process. That means that they can build on what they know each year. But I know this is why we're all here today. And it's that 5th grade science exam that's changed quite a bit. And it's changing not just in New York, but across the country. And that shift can feel really intimidating, especially for your students. But it also really creates this opportunity to make sure that we are actually cultivating the sort of skills our kids need for a future that, can be really uncertain. So it means that we can make our students test ready and future ready. And the thing that we kind of all know already is it's really, you can't do that just through worksheets and memorization. So at LYI, we believe that the way to do that is actually through those joyful hands-on projects where students actually engage in all 8 of the science and engineering practices. And that is what we're going to dig into together today. So this is our agenda for this webinar. The first thing we're going to do is we're going to look at what has changed on the New York Science exam and why it matters. Next, we're going to dig into the science and engineering practices that now make up over half of the assessments. And then you'll step into the shoes of a learner a little bit as we walk through our parachutes unit to see how hands-on learning can actually prepare students for the test. So I want to start with 2 sample pages from the 2017 New York State Science exam. Some of you probably remember this test quite well. I mean, it was around for a long time. And the test had 2 parts. You had 30 multiple choice questions, just like the example on the left, and then 15 open-ended questions like the example on the right. And one thing that you notice here is that the questions jump quickly from one topic to another. They don't stay on a topic for, any length of time. And they mainly ask students to recall basic facts and scientific definitions. So in this kind of test, content knowledge was definitely king. And it made sense that students mainly could prepare through memorization. So now here are 2 sample pages from the 2024 grade 5 science exam. So first of all, I know it's a wall of text. That is intimidating especially if you haven't done things like this before. But moving beyond that, I want you to look at the questions, because you notice how questions form a connected cluster around the same phenomenon. So here it's dropping a golf ball from different heights and then observing how this affects speed and energy. So now, rather than testing isolated facts, students have to analyze data, interpret evidence, and they have to apply that understanding to a real-world scenario. And that's really because more than half of the exam now measures students' ability to engage with the 8 science and engineering practices. And this is why the new tests look the way they do. They are asking students to use scientific thinking within a written test format. That is really difficult and can be incredibly intimidating without a lot of practice. So we've got asking questions and defining problems, developing and using models, planning and carrying out investigations, analyzing and interpreting data, using mathematics and computational thinking, constructing explanations and designing solutions, engaging in argument from evidence, and obtaining, evaluating, and communicating information. These are all things that students are going to be doing on the test. So how do we prepare students for this new approach? We believe that the best way we can do this is by providing opportunities to really engage with those SEPs through hands-on student-led learning. Because when students conduct experiments and collect and analyze data and communicate their findings, they are building exactly the skills that are measured on the exams, but they're doing them in meaningful and fun ways. Okay, so let's move from theory to practice. I'm going to have you step into the shoes of a learner, and we're going to walk through lesson 1 of our parachutes unit. So this unit has versions for grades 2 to 3 and 4 to 5, and we are also developing a middle school version. So I'll flag where the lessons differ by grade band. So we start with this image here. My friend is a toy inventor working on a new project. We get to watch this clip. And as you watch, I want you to think about what you see going on and what questions you might have, what you might wonder about. And then the next thing we do is we introduce the object itself, the invention. Have any of you ever seen an invention like this before? Do you know its name, right? So obviously it's a parachute. Some kids may know this, some kids may not. We talk a little bit about what do parachutes do, right? We're asking students for their own ideas and they give us ideas and then we sort of work through them. You know that parachutes help people or things fall slowly from the sky and land safely. And we talk about who uses them. You know, skydivers use them to land safely. And parachutes are also used to deliver supplies during natural disasters. There have been some companies that actually use parachutes to deliver packages to your house. So some kids might have maybe experienced that. Then we go into a little bit about the history. So think about when you think parachutes might have first been invented. If you have an idea, you can put it in the chat. But I would say legend says, we're not exactly sure, but legend says that hat might give you a bit of a clue. Around 200 AD, there is a story about an ancient Chinese prince who may have made the first parachute using a whole bunch of bamboo hats to escape a fire, which would be pretty cool. Uh, Maybe some of you have heard about Leonardo da Vinci, right? So in the 1500s, he drew a parachute design, but he never built it. So he never knew if it worked. It wasn't until about 200 years ago when a French balloonist invented a parachute that's very similar to the ones that we use today. This guy used it to jump from 3,000 feet and he landed just fine. So, you know, we're still using that basic design now. NASA even uses parachutes to land rovers on Mars. So now we want to return to that toy inventor and notice that before we said, you know, what do you notice? And now we're framing it as the problem. So this is now the problem. And we ask students, so what toy do we see in this clip? It's a parachute toy, right? So the issue is this. Kids really want a fun parachute toy that they can use to float their toys down from high places like stairs or bunk beds. So the inventor is working on a new parachute design that can carry a small toy just to do that. But there is a problem. And this is where we ask students, what on earth is wrong? And this is where kids can give their own ideas and talk about it. Really, pretty much, it's easy to see. The toy parachute is falling way too fast, right? So when the cup lands, the ball tumbles out. So our mission is to help the toy inventor by designing and building our own toy parachutes that can fall slowly and land a ball safely. So as inventors, before we can solve the problem, we need to know the criteria. And that's just the goals that our parachutes need to meet to be successful. So a successful toy parachute here is going to have 3 criteria. The first is it has to have an open cup with nothing covering the top. And that's because you want to be able to put a toy in and take it out quickly. It has to float in the air for at least 2 seconds. And that may seem like no time at all, but I will tell you, it is actually quite a challenge to get these parachutes to float for 2 seconds. And the last thing it's going to have to do is it's going to have to keep the ball or the toy safely inside from start to finish. And again, that's because when kids play with this, we want them to know that their toy is going to be safe. So we're going to be using the engineering design process. That's just a series of steps that inventors and engineers follow when they want to solve a problem. So we've already done that first step. We've already identified the problem. And for the next 5 lessons, we're going to research how parachutes work. We're going to do a lot of making, and we're going to do a lot of experimenting and testing and timing and all this good stuff. And then when we're done with that, we'll be ready to design and build our own toy parachutes. So you can see here in lesson 1, students engage in asking questions and defining problems. They identify what's wrong, they establish criteria for success, and they frame the engineering challenge that they're going to work toward throughout the unit. Okay, so now we're going to step back into the shoes of a learner. So these teachers are all by themselves, like in individual spaces, I believe. Is that correct? Yes, okay. So we're going to conduct this short investigation, and I hope if you brought your paper with you, that would be great. So if you have 2 pieces of paper, that's wonderful. The first thing I want to do is I want us to make a prediction. If I have 2 identical pieces of paper and I crumple one into a ball and leave the other flat, what do you think will happen if I drop them from the same height? So which paper shape will fall the slowest? So students on their worksheet would be circling their predictions. And so you can think about your prediction and think about how your students will respond to the task of explaining their reasoning. And you can put anything you'd like to also in the chat. If you want to put any reasoning that you think or your prediction, that'd be great. Okay. Then it's time to investigate. So you're going to take your 2 sheets of paper. You're going to crumple one into a ball and keep the other one flat. And then I want you guys to take turns dropping them both at the same time from the same height. So you can stand up to do this, or if you're sitting down, you can do it from your seated height. And you're going to drop them. You want to make sure that your arms are in the same place, so that because we're doing a fair test here, right? And you're going to drop them and then watch closely which paper hits the ground first and which falls more slowly. And the deal is, this is a turtle race. Most races, the fastest object wins, but in this one, the slowest object wins. So let's see how you guys do. I'll give you 1 second. All right. So there is the turtle race, and kids get to do this too. And then we get to talk a bit about what happened. So what did we discover? So which paper fell the slowest? Did the crumpled ball fall the slowest? Or did the flat sheet fall the slowest? It was the flat sheet, right? And again, most kids are not going to be surprised by this. It's not, you can sort of intuit what's going to happen. But here's the thing. It's not just what happened, but why? Why does that happen? And asking those questions are the things that really start kids' gears turning. Well, first of all, both of those sheets of paper fell down, whether they were crumpled or flat, right? So why did they fall down anyway, right? Has anybody heard of gravity? So gravity is, it's that force that pulls things down towards Earth, right? So for instance, if you throw a ball up into the air, it comes down. That's gravity. It's why if you jump in the air, you do not go floating off into space, you land back on the ground. That's gravity. So when we dropped those papers, it was gravity that pulled them both down to the ground. So gravity's pulling everything down to the ground. But if that's the case, then why did the flat sheet fall more slowly than the crumpled up sheet? And this is a great place for you to give your kids time to talk about this stuff, right? To give their guesses. I mean, really, the answer is air. Air is all around us. It's the stuff we're breathing right now. And it's made up of teeny tiny invisible particles called matter. Even though we can't see it, when we move through air, we push on it and it pushes back on us. It's just so little and so light that usually we can't feel it. But I can imagine that you might can think of a time that you did feel air push back on you. If any of you have ever been on a bicycle speeding down a hill, or if you've been on a swing and you're going higher and higher, or if you stick your hand out of a car window, right? This push that you feel from the air is called drag. And drag is a force that pushes against the way you're moving. And drag is what slows you down. So if we're thinking again about how air helped that flat sheet of paper fall more slowly, it's all about the fact that the flat paper has more area or space for the air to push back up on. It's that bigger push from air that creates more drag, and more drag is what makes that flat sheet fall slower. So for second and third graders, we support those students in constructing explanations through a class discussion. So we review what happened and what they learned about air and drag that explains why. And then students can write or draw their own explanation. So by the end of lesson 1, students have engaged in 3 more SCPs. They've carried out an investigation, they've analyzed and interpreted data from their turtle race, and they've constructed an explanation. So for fourth and fifth graders, we take the investigation one step further with a timed test. And again, this is a fair test. The only variable that changes is the shape of the paper. Everything else stays the same. Paper size, paper weight, drop height, and drop method. So teachers set up a drop zone for testing, and you can use a wall mark with a piece of masking tape or something like that. And that needs to stay the same for every single test just to ensure consistent drop height. And it also keeps the tests fair. So the teacher does the dropping, and then students can use a stopwatch to time the falls. So this is something that you guys can definitely do. And then after they do this, students analyze the timing data displayed first as a table and then as a bar graph. And we ask students, which is easier to read, right? What gives you more information quickly? Why do graphs help us? So this discussion really helps students see how visual representation reveals patterns much more quickly than just the numbers alone. And we also include the option for students to create their own bar graph using class data. Again, they're doing things that they're going to need to be doing for the test anyway, but they're doing it in this very meaningful way. They're constructing a bar graph out of data that they just saw. And then just like in the younger grades, we end with a discussion that supports students in constructing a written explanation. So for fourth and fifth graders, we add a third question, which is what evidence backs up this claim? This introduces 2 more SEPs, using mathematics and computational thinking through timing, measurements, and graphing, and engaging in arguments from evidence when backing up claims with data. So that's the end of lesson 1. In lesson 2, this is where students get to take some inspiration from nature. So they build 3 seed-inspired paper flyers. It's called the fish, the maple seed, and then the dandelion. And they investigate how shape affects the way things move through the air. Then in lesson 3, students work in groups of 3 to build and test parachute models using everyday materials. So there's coffee filters, pipe cleaners, and a small cup. And each student is going to build the same model except for one thing, which is the canopy size. So every time we test, we change only one variable and we talk a lot about what makes a fair test. And then in every investigation, we always ask students to compare and predict. So for this investigation, before they do any testing, students compare the 3 sizes of the coffee filters. They talk about what's the same about them, what's different, and then they make another prediction of which canopy size will make the parachute fall the slowest. So after comparing and contrasting, each student builds a parachute model following the step-by-step instructions. So here in his example of the maker videos that we include as part of the lessons, and we have maker videos on pretty much every step of the building process for every lesson. So this video is on how to make the canopy.
Step 2, make the canopy. We're going to tape 4 pipe cleaners to our coffee filter canopy. Grab one pipe cleaner and place a piece of tape over the very end of it. Place it on the edge of the coffee filter closest to you. Now for the most important part. Use your fingers and fingernails to scratch and press the tape down into the pipe cleaner and coffee filter. This will make sure the tape sticks properly. For your next pipe cleaner, you'll look directly across from the one you just added. You'll tape down a pipe cleaner again, making sure that you press down the tape. For the next part, you're going to turn your coffee filter so the pipe cleaners are sticking out from side to side. Then, just like a plus sign, you'll add 2 more pipe cleaners directly across from each other, just as you did before. When you're all done, your canopy should look something like this, with 4 pipe cleaners sticking out around the sides.
So these are videos that you can use. You can repeat them. You can use them with the sound off later on for kids that need extra support. They're really great. And the nicest thing that we found is that having that video on the screen at the front of the class is so big and so clear. It just makes it much easier for kids to be able to understand what they're going to do rather than have, just the teacher in the front trying to show everybody what they're supposed to do. So once we play the video, there's a review of the steps that you display on the screen, just again, to support that making process. And you can go back and forth as many times as you need. But we find that playing the video first, having everybody watch it, and then having them build, you can build with them with that slide that's there now, really helps quite well. So once they've built all of their parachutes, in their groups, students observe how the parachute falls through the air, what happens to the canopy as it falls, how the cup hits the ground, and if the ball stays in the cup. And they write all of their observations on their worksheet chart. So for the upper grades, we once again run official timed tests using the same drop-down zone setup from lesson 1. And again, it's a fair test where only the canopy size changes and everything else stays constant. Again, this way we know that any differences that we see are caused by the canopy size and not something else. So we run 4 tests. We run the ball alone, which is just the baseline of what would happen if you didn't have any parachute at all. And then we run small, medium, and large canopy tests. In each test, we do 3 trials. Why 3? Because we know that testing multiple times helps find the patterns that you need to see. And it also builds confidence in your conclusions because there's always some natural variation. And what you notice maybe in the patterns, right? If you can look here on the screen, maybe this is something that you might have figured out already too, right? So not surprised, the ball alone fell the fastest. It falls about half a second. And you can see the small and the medium canopies actually perform pretty similarly. They take about 1.4 seconds to get down. But that large canopy, that's a big difference. It stays up almost 1.8 seconds. That's nearly half a second longer. And again, we're talking about bits of seconds here because these things fall so quickly. So in every lesson, we use visual diagrams to illustrate the science concepts behind what students observed. So we review prior learning and we introduce new ideas. So just like you saw in lesson 1, in lesson 2, we'd be talking about, after they've done all of these experiments, talking more about what is actually going on. Why does the larger canopy work so much better? I guess its bigger canopy gives you more drag because, again, there's more area. And then we also display data as both a table and a line graph. And the line graph is really interesting. Number 1, it's on the test. But number 2, line graphs actually organize data. You can organize data here by canopy size and trial number, so you can do more than one thing. And that shows how each canopy performed across tests. And you can really see the variation between the trials too, right? And you can see that's a great way to visualize why you test multiple times. But it's also a really great way to look at the patterns, right? If you look at the patterns there's almost no difference between the small and the medium canopies. But there's a big jump when you compare the smaller sizes to the large canopy. So what we're hoping students get out of this too is this key insight that you really need a big difference in surface area to see a big change in drag. So then we end this lesson with a discussion that supports students in constructing a written explanation. So again, in lesson 3, Students develop and use models by building parachute prototypes. They plan and carry out investigations with controlled variables and multiple trials. They analyze and interpret data through tables and line graphs. They use mathematical and computational thinking through timing measurements and graphing. They construct explanations like, about connecting the canopy size to surface area and drag. And they engage in argument from evidence. So when they're backing up claims with data, they know what they're doing. In lesson 4, this is where students investigate how suspension line materials affect parachute performance. So again, we started with the canopy, that's the top of the parachute. Then we moved to the suspension line, that's the middle part of the parachute, and they're really important as well, right? And those materials can affect parachute performances in different ways. So students are learning about all the different parts of the parachute and how they work together. In lesson 5, students think about solutions for keeping the ball from rolling out of the cup by adding a landing base. So again, now they're looking down at the bottom of the parachute because this is what we need to do in order to be able to fulfill all the criteria. The trick is that when you add a landing base, you're adding weight. So that can also change the time. So there's all these different variations in this that get kids thinking about all the things that they have to make and the complexities, but in a way that they can really understand. So by repeating this process with the different variables, students really build fluency with those same 6 SEPs. They're doing the same kind of stuff with different variables in slightly different ways, but every time going back to the same patterns, constructing explanations. We're doing all the stuff at the end as well. So now is where students move from research to their own design. So we spend 5 lessons in the origination phase, and this is where they apply everything that they've learned to solve the toy inventor's problem. So I know we've covered a lot here. For the next few slides, I'm going to kind of breeze through the rest of the process. So in lesson 6, students partner up to design their own parachute. They review each part of the system, they sketch their ideas, and then they share with another partnership. So they're making a case for how their design will meet at least one criterion. And again, they're doing their own argumentation, they're making explanations. They need to figure out how to explain why they think something is going to happen. Lesson 7 is Build Day, and this is where partnerships bring their designs to life. So this is where you'll hear students naturally use the vocabulary that they've learned. Like I always hear students saying things like, well, we need more surface area, or this material adds too much weight. And the nice thing about being able to hear students say those things is that that's actually where you fully understand that they're really developing models and communicating scientific information almost without even realizing it. They've internalized all of the stuff that they've learned. And now that they get to use them, you can see all of that knowledge come out and they get excited by it. Then we have the moment of truth in lesson 8, which is testing. So this is where teams conduct their first official trials. They time how long their parachutes float. And this is where they note the problem. So this is also where you'll hear kids say things like, oh, the ball keeps falling out, or we're not at 2 seconds yet. We've got like a little bit of time to go. So again, they're using the language, they're figuring out what's going on, they're using this evidence plus their research in order to plan specific improvements. So they figure out what they need to do in order to improve their design. Then when they compare their students with another team, they work to explain why one design met a criterion that the other design didn't. So they're making more of those arguments from evidence, but they're doing it from the context of their own experience. So it's really meaningful for them and they have a reason why they're doing all of these things. Then in lesson 9, teams roll up their sleeves, and this is where they modify their parachutes based on their redesigned plans. This is really exciting for me always because you can see the scientific thinking happening as they make these targeted improvements. When I've taught these classes, I walk around and watch students. I mean, they're changing the sizes of their canopies, or they're changing the length of their suspension lines, or lots of them are like just taking the landing base off completely and making a very different, lighter landing base. They're doing all of these things. There's a real buzz in the classroom. it's an excited hum of activity, and it makes me like, I don't know, I always feel really happy about that just as a teacher. So the unit then wraps up with final tests and formal presentations. And this is where students use their worksheets as evidence to explain their process. So they compare their first prototypes with their final prototypes, and then they argue why their final design improved. And these presentations, when I've seen them, they show deep internalization. This is not just students reciting facts. This is students standing up there telling the narrative of what they just experienced. You know, they're explaining how gravity, air, and drag affected their designs and what they had to do to overcome the challenges from that first design to the second. Like, you can always hear kids say things like, our first design, stayed up for 1.2 seconds and the ball kept rolling out. But then we decided to make the canopy bigger and we added a wider landing base. So our final design actually stayed up for 2.4 seconds and the ball stayed in. So we met all the criteria. The end of the unit also includes a knowledge snapshot, just a very short summative assessment that's modeled on the state tests. So students can practice these questions, the types of questions that they're going to see in a low stakes environment. And we also include that throughout the whole process in the worksheets so that it's not a huge amount. It doesn't feel like cramming for an exam. It feels like the natural writing extension of something that you've just done. And doing it together over and over in these ways in easy, digestible periods, I think really helps students see that these questions don't have to feel intimidating. They're really actually great questions that once you know what the procedure is and you know how to read them, then you're good. You know what you're doing. So this completes our walkthrough, and my hope is that you leave today with some concrete ideas for how you can use hands-on engineering design challenges to create opportunities for students to meaningfully engage in all the 8 SEPs. So, a lot of what we walk through is geared toward 5th grade, but ideally what you do is you start early. You start all the way back in kindergarten, and you keep on introducing and reintroducing all the SEPs in age-appropriate ways that build over time. And in that way, our belief is that if you start with stuff like this in kindergarten and just give them little bits that they need that they can handle, and then you add a little bit more to that and reiterate 1st through 5th grade, especially in 4th and 5th grade, by the time you have to add some more of the heavy lifting, the writing, the other questions and the thinking, they have already done so much work before then to prepare them. They're scaffolded fully. And then it's just a matter of telling kids, we're just doing the same things we did before. We're just extending it a little bit. And the hope then is that by the time they get to the 5th grade exam, that they don't feel intimidated. And they're not looking at this wall of text going, I don't even know what I'm doing. They're instead going, oh, I got this. We already did this a ton of times. And I feel like that's really how you get this kind of learning joyfully integrated into the kind of testing that students need to take. So our approach focuses on engineering processes and projects that hold natural interests for kids. So each unit is developing these SEPs through activities that hook into children's curiosity. And again, by the time they hit 5th grade, they practice these thinking skills for years. And again, when they see test questions asking them to interpret data or construct explanations, all they'll see is processes that they recognize, that they've used in projects that mattered to them. So for me, I believe, and the League believes, that this is really how we transform test prep from memorization into joyful, inquiry-driven learning. And that is it.
Amazing. Well, oh my goodness. Thank you so much, Kira, for that insightful and inspiring presentation. It is incredible to see how the League of Young Inventors is helping students build their confidence and by, real world problem solving skills and building through hands-on engineering and invention. So thank you so much for that. Now it's your turn, our amazing audience. If you have any questions, please type them into the chat right now and we'll answer as many as we can. I do want to start with one question and give some time for our audience to type in. So my first question would be, uh, after the thorough explanation of what the units entail, which is amazing, and how does the league how do the League of Young Inventors units fit into an already full school day? And what kind of flexibility do teachers have when pacing the lessons? And this is coming
Yep,
from a former teacher who, just sometimes we don't have enough hours.
absolutely, totally. Well, one of the nice things about this is that it is really, I think it's really pretty easy to insert into what is definitely an already busy day. We are not a replacement for science curriculum. We are an a sort of like an addition, a boosting of the science curriculum that already exists. So that's one way of thinking of it. These lessons, each lesson is designed to be 45 minutes. Some lessons can definitely be broken up into two sections. And again, because there's not a huge amount of lessons, you can do it in a number of different ways. I've had teachers who have gone through it like in a 4 or 5 weeks, and they've just made whatever time they've got to do it. And I've had teachers who've taken a lot longer, that they've done like one lesson a week. And some of them have done that lesson split into two. So they've got 20 minutes here, we'll do part of it here, and 20 minutes here, we'll do part of it here. That's the other nice thing, is that the way that we've split the lessons, a lot of the time you can split the building and then refer back to it later on with the science explanations. So that's another way to be able to do it as well.
Amazing. Well, that is very important. So thank you for that and clarifying that for teachers. I do have another question. How does how do your programs support students with different learning styles or varying levels of prior STEM experience, specifically, especially in K-5 classrooms?
Yeah, this was really important for us as we were developing these units, because we know it's one of the things that I noticed as a teacher too. A lot of times when you have project-based learning, you kind of get this problem that everybody then immediately has to start figuring out how to solve. And that can be really intimidating for kids, especially younger kids, because they just don't have a huge amount of life experience to draw from. And then you add that with, sometimes you've got some kids who've taken a whole bunch of classes or done stuff with their parents and museums, and other kids who have not. There's a real it can feel really much more intimidating for kids who don't have as much. So this is why we actually have that huge research uh, portion of the unit. The research lessons are designed to get everybody up to the same speed. So if you don't know anything about parachutes, you will have everything that you need to be able to build a parachute during origination phase. And if you already knew everything you thought you could know about parachutes, you will probably still learn something else that will help you make a parachute in origination. This is also why we do all of these, all of the builds are very much like, they are the same. We're making the same thing. Students are using models that are basically created by the league. We do this to give students a lot of experience in cutting and taping and all of that. We also do it because you have to have the same kinds of things to be able to test against each other, because we're trying to make it as fair of a scientific test as possible. And the third reason we do it is because all of that experience allows everybody, again, to be kind of on the same page by the time they start making. So even if you were a kid that had very little experience in cutting or taping or, fashioning things together, by the end of that research phase, you will know how to do all of these things. The other thing that I think really helps a lot, besides all the practice, is those visuals, the videos that we include. It's so much nicer to have it up on the screen. When I used to do this myself as a teacher, I would constantly be having to like show everybody, and then you have to show them over here because kids in the back couldn't see. And it's really hard, I think, to be able to get that kind of understanding throughout a whole classroom of kids if you're just doing it yourself. So with the videos, the great thing is they are incredibly visual. They're like just close up of what you need to do. Sometimes when I've used them with classes, if kids need an extra, an extra viewing, I'll just turn the sound off. The sound isn't even necessary most of the time because the visuals themselves are so clear. It helps also with kids for whom English is not their first language or who have maybe some language processing differences, that you can just watch the video and that helps you learn how to do the stuff.
That's amazing. Yeah, it sounds like you pretty much thought of all of it. Love
We
it.
tried.
And okay, I have one last question, but not least. What feedback have you received from students about these units, and how have you seen their confidence and engagement change over time?
I think, we've received really positive feedback from both teachers and students. And the thing that I think is probably the best feedback of all is when I've taught these lessons myself to students, and then when I go into classrooms where students have been working with teachers on the units that we've created. The best part is just I don't even know if we could call it feedback. It's just the reaction of students to the material itself. Going in there and not seeing kids who are just kind of listening passively or kind of bored. Going in there and hearing that like hum. There have been times where like kids cheer each other. You get to the point where like you're doing a parachute or a floating boat and somebody makes they get all the criteria and everybody erupts into cheers. And conversely, you get things where someone doesn't meet all the criteria and everybody's like, that's okay, this is what we think could happen. So it's a lot of it is just the fact that students are absolutely embracing what this is all about and internalizing the emotional support that they can give each other and the sort of confidence that they're building in themselves, the ability to make a mistake and know you can fix it. And that's a big deal too. At the end, I think watching kids give their presentations is also like one of the biggest positive feedbacks for me, because you really see these kids talking very proudly about what they make, and they're using all the language that we want them to use. And they're exactly explaining in their own words, right? It's not a rote memorization thing. They're explaining how gravity works and how it affects, what they did. Or, they're explaining drag, and how that affected their fall time and what they had to do to create more drag. And you can get this from second graders. It's really great.
It's fantastic. Um, well, I could hear you speak about this all day. I just love it. And but once again, I want to give a huge thank you to the League of Young Inventors team and to you, Kira, for a fantastic presentation and also for the questions from our audience. We hope that today's webinar sparked new ideas for bringing authentic STEM and engineering experiences into your classrooms. So, if you're interested in learning more about the League of Young Inventors and how their curriculum can support your teaching goals, you can now find their products also at the WhyMaker website, and we encourage you to connect with us to explore their programs further. Now, before we wrap up, don't forget to follow the League of Young Inventors on social media, as you can see their handle on your screen, as well as WhyMaker. And yeah, to continue seeing inspirations and classroom resources. And also be sure to subscribe to our newsletter so you don't miss our upcoming Lunch and Learn webinar sessions. So once again, thank you to Kiera and to all of you for joining us today. We truly appreciate your dedication to empowering the next generation of inventors. Have a wonderful rest of your day, and we hope to see you at our next Lunch and Learn.
Thank you.